that work? All right, the first method we're going to go over is method number 6, difference of two squares, the dots. So if you look right here, we have Miss Jones wrote a lot of things multiple times. So we're going to just make all of these A's. There we go. So we have a squared minus 1, and we're going to rewrite it as a squared plus 0, a minus 1. Okay, what this is asking us, remember, it's asking us what multiplies to equal -1, but adds to equal 0. Okay, so I'm looking for two numbers that will multiply to equal -1, but add to give 0. And the only possibilities for that would be a minus 1 and a plus 1. Okay, and that's because we need to be able to equal 0. All right, so let's try it again here. Now I have 9b squared minus 4. So if you look at it in terms of a trinomial, I am missing my b term, minus 4. So in this case, I'm asking what multiplies to give me -36b squared, but adds to give me 0b. So it multiplies what adds. And again, it's going to have to be a -6b and a +6b. Okay, B's and 6's probably weren't a great idea, but here we are. Okay, so if I'm going to use the box really quick. And I'm going to put in my first term, which was 9b squared, and my last term, which was -4, and my b's that make it work, which is -6 and +6b. Okay, my greatest common factor of each row and each column. So we have 3b, we have -2, 3b, and +2. So my factors are 3b plus 2 times 3b minus 2. Okay, so let's look at what we have here. If you look here, we ended up with the first and second terms repeating themselves, but different operations. Here, same thing. We had the first and second term repeating themselves, but different operations. Okay, the other thing that we can take notice is that we're dealing with perfect squares. 9b squared and 4 are perfect squares. A squared minus 1 is also 1 is a perfect square. So this is where our rule starts to fall into place. Someone said, okay, I've done enough of these to come to a conclusion. And the conclusion is that when you have difference of two squares, we are looking at the first term and the second term. And first thing we're doing is we're going to check, are they perfect squares? So if the first and second term are perfect squares, I don't know why I put an extra e in there at the wrong spot, squares. And then 2, am I subtracting? If this is true, then all I'm doing is looking at the roots of these perfect squares. So for example, x squared and -9, x squared and 9, they're perfect squares. Check. Is it being subtracted? Check. So therefore my factors are x minus 3 and x plus 3. Okay. All right. So at your table, I want y'all to kind of talk about out loud what the possibilities, what the factors are of the remaining 8 polynomials are, and we'll go from there. All right, so let's see how you all did. So again, checking the rule, perfect square, check. Subtracting, check. So we have x minus 5 times x plus 5. Okay, perfect squares, check. Subtracting, check. So we have y minus 8 times y plus 8. 4a squared minus 9, perfect square, check. Subtracting, check. So we have 2a minus 3 times 2a plus 3. Okay, 49x squared minus 1, perfect squares, yes. Subtracting, yes. So we're left with 7x minus 1 times 7x plus 1. All right, 9x squared plus 16b squared. Perfect squares, check. Subtracting, womp, womp, womp. It's not subtracting, it's addition. And because these two terms have nothing in common, therefore this is prime. All right, perfect squares on G, yes. And so you Are they being subtracted? Yes. So you should have gotten 6m minus 10n times 6m plus 10n. All right, this is where a lot of y'all freak out at. Fractions. Fractions are our friends, okay? When you're trying to decide if a fraction is a perfect square, you're going to look at the numerator and the denominator. If the numerator is a perfect square and the denominator is a perfect square, then the fraction is a perfect square, okay? So as you can see here, we have 1 over 4. Well, the square root of 1 is 1. Square root of 4 is 2. So therefore, 1/4 is a perfect square. So we have 1/2 x minus 1 times 1/2 x plus 1. Okay, same thing here. Even though it's switched, do I still have two perfect squares being subtracted? And the answer is yes. So when I factor this, I get 8 minus square root of 9, square root of 25, 3 over 5a times 8 plus 3 over 5a. Okay, all right, so hopefully you all did well. And you're like, yes, I got this, okay? So we're going to conclude. So in conclusion, if the A term and C term of what would be a trinomial are perfect squares, then you factor them by taking the square root of each term and add and subtract their roots, okay? So you're taking the square root of each term and adding and subtracting their roots, okay? All right, so what I would like for you to do is to practice it. So you have 4 practice problems for today. X squared minus 9, d squared minus 121, 9h squared minus 144, and 25k squared minus 64j squared. Okay, you're going to complete these 4 practice problems and then check with the peer, a table mate, to make sure you did it correctly. All right, awesome. Okay, our next part, we are at method number 7, difference in sum of 2 cubes. Docked and socked, okay? Difference in sum of 2 cubes. So sum or difference of cubes depend on both terms being perfect cubes, okay? When we say perfect cubes, we got to kind of think about what that means. A perfect cube means a number times itself. So in sense of volume, so if I'm taking length, width, height of something, 1 times 1 times 1, that makes a cube, right? 2 times 2 times 2, that makes a cube, okay? So some of our common perfect cubes are 1 times 1 times 1, which is 1, 2 times 2 times 2, which is 8, 3 times 3 times 3, which is 27, 4 times 4 times 4, which is 64. And we have 5 times 5 times 5, which is 125. That's kind of all I got for you right now, but you get the gist of it, okay? These are some of our common perfect cubes, okay? So how does this work? There are 2 rules. Because they're cubes, you can actually have a sum and a difference, and it will work, okay? The sum and difference are going to create binomials. A binomial times a trinomial. Remember, binomial because you have 2 things being added. A trinomial because you have 3 terms being added, okay? And they each have their rules. So if it's adding the 2 cubes, then your binomial is going to be positive. Your trinomial is going to be negative positive. If it's subtracting the 2 cubes, then your binomial is going to be negative and your trinomial is going to be positive, positive. Okay, so look here, we have 8 cubed plus 1. 8 cubed plus 1. To find my a, I'm taking the cube root of 8x cubed. So a in this case would equal 2x. To find my b, I'm taking the cube root of 1. So my b equals 1. Once I have my a and my b, I am just plugging them into the formula. Okay, so we have a plus b. Then we have a squared minus a times b plus b squared. Okay. Now the same thing applies here as far as taking the cube root, but this time I'm subtracting. So it's going to be a minus b times a squared plus a times b plus b squared. Okay. All right. Let's do a problem from scratch. So here we have x cubed plus 27. X cubed plus 27 lets me know that I'm looking for the sum of 2 cubes, okay? So the first thing I want to make sure is you're going to always check for GCF. Is there a greatest common factor? And the answer is no. So I'm good to go. So I'm going to find my A. A equals the cube root of x cubed, which is x. B equals the cube root of 27, which equals 3. Now I have my A and my B, so I'm just going to substitute them in. So we have x plus 3 times x squared minus x times 3 plus 3 squared. I'm going to simplify this. X plus 3 times x squared minus 3x plus 9. Okay? And bam. There is my factored trinomial, my factored perfect cube. All right, let's try another one. So this time I have 8x cubed plus 125. Okay, so again, I want to check for GCF. If there isn't a GCF, then we're good. First, I'm going to identify my A. My A equals the cube root of 8x cubed, and my B equals the cube root of 125. The cube root of 8x cubed is 2x. The cube root of 125 is 5. I now have my A and my B. And again, I am using the sum, so I'm plugging them into this formula. So we have 2x plus 5 times 2x squared minus 2x times 5 plus 5 squared. I'm going to clean that up. And we have 2x plus 5 times 4x squared minus 10x plus 25. And that is my factor. Okay. Some of you are probably wondering, why are we stopping here? Well, I can't factor this any further. There is nothing that multiplies to give me 100, but adds to give me negative 10. Okay. And that's what's going to happen every single time. I can't factor past this. This is a non-factorable trinomial. So that's where I stop at. Okay. All right, let's do a difference. So notice on this difference, again, you want to check for your GCF. This time I actually have a GCF and it is 3. So I'm going to divide out my GCF first. 3x, I'm sorry. It's 3x. I'm going to divide out my GCF and I'm left with x cubed minus 1. Okay, now I'm going to go ahead with my A. My A equals x, my B equals 1. So I am using difference now, so I'm following this formula. So I have x minus 1 times x squared plus 1x plus 1 squared. My final answer has to include my GCF. So my final answer is 3x times x minus 1 times x squared plus x plus 1. Okay, so there's my final answer. All right, we're going to do one more together. Well, no more together, and then you're going to do 2 more. We're going to no more together, and then you're going to do 2 by yourselves. Okay, so conclusion: if the A term and C term are perfect cubes, meaning that if this was a trinomial, if the first term and the last term are perfect cubes, then you factor them by taking the cube root of each term and follow the pattern to create the binomial and trinomial factors. So again, you're following that pattern for A cubed plus B cubed equals A plus B times A squared minus AB plus B squared. And for A cubed minus B cubed, it equals A minus B times A squared plus A times B plus B squared. Okay.